Welcome back to part 3 of our lesson on trigonometric functions. At the end of the last video, we finished off discussing how we might evaluate our 6 basic trig functions at any angle. This means angles that could live in quadrants 1, 2, 3, or 4, whether that angle was positive or negative. It really all came down to, can you draw and graph the angle on a Cartesian coordinate system, then subsequently draft the corresponding reference triangle, figure out the side lengths of that triangle using either a 30, 60, 90 or 45, 45, 90 triangle, and then determining via ASTC whether the sine, cosine, tangent, or their reciprocal counterparts were positive or negative, and then using their quotient relationships with the sides of the triangles to figure out what the final answer was. But at the end of the day, what we've really done is defined brand new functions. They're functions that have their own properties. We spent all of chapter 1 learning about the different properties of different functions. We then talked about chapter 2 where we said, okay, cool, we have all these interesting, functions ahead of us. We have polynomials. We then talked about rational functions. And then in chapter 3, we introduced exponential functions. And every time we introduced a new function, we asked very similar questions about it. We had questions about, for example, what are their domains and ranges? We had questions about whether they're even or odd. What's the parity of the functions? And then eventually we moved toward conversations about whether the functions are one-to-one, therefore invertible. If they're invertible, what's their inverse? We then also spent so much time talking about how to graph functions. So in this world of trigonometry, the reason that this takes place after the conversation of precalculus is because we have to import all of those same questions, but now we're going to try to answer those questions as they relate to trigonometry and the trigonometric functions. So it'll be in the very same spirit that we've already been working in this semester. The only difference is now with brand new functions that we've constructed from scratch. To begin with, let's talk about some domain and range. The properties that we want are the following. The domain of sine and cosine is going to be negative infinity to infinity. Note that when I say this, note that the x here is taking the place of the thetas on the previous page. So when I say negative infinity to infinity, this means angles as they're given in radians. So for example, like we saw in a previous lecture, the angle theta is equal to pi is going to be thought of as the angle that's approximately 3.14 on the real number line. So when I say negative infinity to infinity, what I mean are things like 3.14 is corresponding to pi, which is corresponding to the straight angles that we kept seeing in the previous videos. The ranges are interesting. Notice that of all the examples we've looked at so far, the sine and the cosines we keep drafting keep looking like things like, we have things like 1/2, things like 1 over square root of 2s, and the commonality between all the outputs that we've developed so far is that all of these are somehow less than 1. It's not even something that we were really interested in focusing in. It just happens to be that that's the case because sine and cosine are computing quotients of side lengths versus hypotenuse. And remember what the unit circle is doing. If I have an angle and then I build a reference angle and then I have sine and cosine are the base and the height respectively. But if this is a unit circle, then the hypotenuse, h, is always a 1. So then, of course, if I build any sort of sine or cosine relationship, then I'm going to have y over 1 or x over 1, but y and x themselves both have to be less than 1. We can see that from the picture. So we can justify that sine and cosine of any angle definitely is going to be somewhere between 1 and negative 1. because of course sine and cosine can be negative depending on the quadrant you live in. Cosine and secant are both going to be even functions. Remember that what it means for an even function to exist is that if I plug in a negative x in for the argument, it gives me back my original function. So therefore, cosine of negative x is equal to cosine of x. And all of the other trig functions, sine, cosine, or sine, cosecant, tangent, and cotangent, are all going to be odd functions. Remember that what that means is that if I evaluate them at negative x, it pops the negative outside. And so I get negative of my function. The even and oddness of a function, of course, is indicative of what type of symmetry that it has. But if you recall, we spent a lot of time trying to make sure we understood the algebraic part, these parts of what it means to be even and odd. And one of the reasons we spent some time doing that was exactly so we could import that information into this conversation. The even and oddness of the functions help you evaluate the function at, say, a negative angle, if, for example, you would prefer to work with positive angles instead of the negative angles. So, for example, here's secant of negative pi over 4. We know from above that secant is an even function. So we have two options. Either I could just evaluate this normally via the information we did in the previous video, or if I remember that secant is an even function, I could rewrite this then as just secant of pi over 4. Then I can evaluate this function. Depending on the context, one of these might be easier for you to evaluate. So if I did secant of pi over 4, I'm going to draw pi over 4. There it is, first quadrant. If that's pi over 4, this is a 45, 45, 90 triangle. So I have a 1, and a square root of 2. And so what I witness is that secant is going to be hypotenuse over adjacent. So in this case, I'm going to end up with the square root of 2 over 1, which is the square root of 2. Whereas alternatively, you could have tried to graph this value right away, and then you would have been negative, which would be clockwise. We'd end up with this angle in the fourth quadrant, where now this is 45 degrees. Again, you'd still have 1 and now negative 1 and square root of 2. But then you'd remember that ASTC, so what that means is that cosine is going to be positive. Indeed, in this case, you're going to have that secant is going to be hypotenuse over adjacent. And so with this explanation, the secant of negative pi over 4 is equal to, again, square root of 2 over 1, which is just square root of 2. And so you get the same answer either way. The only question is, do you want your angle to be in the first quadrant or the fourth quadrant? And if it doesn't matter, then no harm, no foul. But there are instances where passing from fourth quadrant to first quadrant can simplify matters greatly. Because, for example, you don't have to concern yourself about ASTC. Here we have sine of negative pi over 4. So it's the exact same angle. So we can actually use the exact same picture if we wanted to. But the key observation is that sine is an odd function. So this is going to be equal to negative sine of negative pi over 4. I'm sorry, a sine of positive pi over 4. And now referencing the same picture from above, this picture right here, we recognize that this is equal to negative sine is going to be opposite over hypotenuse. So here we'll get negative 1 over square root of 2. Whereas instead, we could have used this picture right here, and we could have said that the sine of negative pi over 4 is equal to, in this case, opposite over hypotenuse, but the opposite is a negative 1 because we live in quadrant 1. So again, we're going to get negative 1 over the square root of 2, which is just negative 1 over root 2. So of course, they're equal, That much we knew because we're told that sine is going to be an odd function, but it does change how you go about solving the problem. So these are going to be the beginnings of properties that we need to understand and to be able to utilize them as they relate to eventual conversations we're going to have where, for example, we're going to talk about how to solve trigonometric equations at some point. These might be relevant when it comes to graphing sine and cosine, because so far we haven't graphed these functions on a Cartesian coordinate system. So what other properties do we have for these trigonometric functions? Well, we're going to introduce now the notion of an identity. Identities are factual equations. We've already encountered a few of them. For example, these identities. These are going to be referred to as the reciprocal identities. These are the identities that tell you what cosecant, secant, and cotangent are equal to. In particular, when I call them identities, what that means is that these are equations that relate one trig function to some other trig functions. And that means, for example, in this identity, no matter what angle x is, you know that on one hand, if you compute its cosecant, you know on the other hand, it's going to be equal to 1 over the sine of that angle. And that's the big key, is no matter, oh, no, don't want to do that. And that's the big key, is that no matter what angle x is, this identity is true. The reason this is useful is because then, in the future, you might run into a situation where you're looking at some sort of a expression that involves cosecants, and then while cosecants might be difficult to work with, you realize, oh wait, I can swap the cosecant out for a 1 over sine, and maybe that simplifies the situation a little bit. So these types of identities are very helpful, and the more identities that we can collect, the more versatile our tool set becomes. We do have what are going to be called quotient identities. These are things like tangent is equal to sine over cosine. If this is at all mysterious why this might be the case, you can justify this a little bit. For example, using x's, y's, and h's, we might remember that sine of x over cosine of x, well, sine of x is going to be opposite over hypotenuse, and cosine is adjacent over hypotenuse. And so if you do this fraction divided by that fraction, keep, change, flip, says that this is going to be equal to y over h times h over x, where the h's cancel. You get y over x, and this is exactly the definition for what it means for a tangent function to be evaluated. I should note that because I'm passing from thetas into x's, there is a little bit of confusion here between the fact that this x is representing sort of an adjacent side of a triangle. This x is representing the angle for that triangle. So maybe in the spirit of clarity, what we'll do is we'll erase these arguments and replace those with thetas. So what I've just done here is I've demonstrated a proof that sine over cosine is equal to tangent. Eventually, we're going to spend some more time on how to develop trigonometric identities, and it's important that we realize at this point in time as we introduce them that identities are true one side to another. You cannot establish the validity or the truth value of a trigonometric identity by, for example, taking what you're trying to prove, sine over cosine is tangent, and then multiplying cosine to the other side. You can't do that. You have to start with one side and then somehow reason your way to the other side in one single equality chain. It's absolutely imperative. So this provides justification for that trigonometric identity. Similarly, you can establish that cotangent is the reciprocal of tangent, so you get cosine over sine instead. And so that'll take care of the quotient identities. And the last set of identities we have is number 3 here. These are arguably the most useful. These are going to be referred to as the Pythagorean identities, eerily reminiscent of the Pythagorean theorem. If you want to verify for yourself why these are true, you might draw the following picture. For starters, we're going to try to argue that sine squared of an angle plus cosine squared of that same angle is always equal to a 1. One way to argue that for yourself is to draw a reference triangle. Observe that no matter what reference triangle you build, if you have an angle theta, you have a base x, a height y, and a hypotenuse h. Notice here that if I wanted to compute sine squared of theta plus cosine squared of theta, we might get, for sine is opposite over hypotenuse, so we're going to get y squared over h squared. Cosine is adjacent over hypotenuse, so we get x squared over h squared. And so here we're ending up with y squared plus x squared over h squared. But you might be asking yourself, where does the Pythagorean part come from? Well, that key observation comes from looking at this triangle we've built and using the Pythagorean theorem. Note that by the Pythagorean theorem, the base squared plus the height squared is equal to the hypotenuse squared. So we can take this information and import it into our proof up above and realize that y squared plus x squared is just h squared. And so now we get h squared over h squared, which is of course a 1. So we've taken the left-hand side of the identity, and we, through some argumentation, have reached the right-hand side of the identity. And that establishes the truth value of this first Pythagorean identity. If now you wanted to construct the second and the third Pythagorean identity, it's simply enough to take the given Pythagorean identity. So let's maybe call this one purple star. If I want to do purple star, what I'm going to do is I'm going to take the Pythagorean identity sine squared, we'll do theta, sine squared theta plus cosine squared theta equals 1. And what I'm going to do is divide both sides by cosine. So divide everything by cosine squared. Divide everything by cosine squared. Divide everything by cosine squared. On the left-hand side, sine over cosine, as we noted, is a tangent. So that's going to turn into the equation tangent squared theta plus, well, those are going to cancel and we get a 1. And the right-hand side gives 1 over cosine squared, which, by the reciprocal identity, 1 over cosine is secant. So therefore, I'm going to get secant squared here. And that is exactly the identity that I wanted to prove in purple. You might now guess that if instead I wanted to do this third Pythagorean identity, which I'll do in green, what I might do is I might take the original Pythagorean identity, just like I did in the previous step, and I might divide everything not by cosine, but maybe I'll divide everything by sine. Now the sine squareds will cancel, and I'll be left with 1 plus, not tangent, but this time cotangent squared. And then on the right-hand side, I'll end up with a cosecant squared. I'll end up with a cosecant squared, which is exactly the identity that I wanted to try to prove. As I mentioned, it might not be clear right now how powerful these identities are, but they are the bread and butter of trigonometry. Well, maybe not that. The trig functions themselves are the building blocks, but this is the way we start sewing those building blocks together. The most prevalent and the most commonly used ones are exactly these identities. And these Pythagorean ones are also infinitely useful, and that's why we spent some time deriving them in the best way we could. On the fly, I do not intend to memorize these second and third Pythagorean identities. I usually go through this reconstruction process every time, because again, I like to minimize the amount of memorization that I commit to. Now, why could these be useful in some way? Well, let's take a look at some examples and we might see some use. So here we're given a sine and a cosine. And we don't know what angle this is, but apparently for whatever angle this is, angle x, the sine is 2/3 and the cosine is √5/3. It turns out that as long as you know two of the trig identities at an angle, you can find the four remaining values. Notably, we still do not know the angle, and in fact, we probably will never know the angle. But these identities give us enough information to work off of. For example, the tangent, as we saw earlier, is the same as sine over cosine, where the sine is 2/3, the cosine is square root of 5/3. Keep change flip says that this is 2/3 multiplied by 3 over square root of 5. So the 3's cancel, and I'm left with 2 over √5. Secant is, by the reciprocal identity, 1 over cosine. But that's 1 over the square root of 5/3, which simply reciprocates it into 3 over the square root of 5. Cosecant is 1 over sine of x, which is simply the reciprocal of sine, so we know that's going to be 3/2. And cotangent, we actually have two options for cotangent. We could take our answer for tangent and then reciprocate it. But that's kind of dangerous, because if you made a mistake in computing your tangent, then if you use that result to do the cotangent, you're then, of course, just going to perpetuate your error. So when in doubt, start with the data that's given to you. So I might just go back to the beginning and recognize cotangent is the same as cosine of x over sine of x, which is the square root of 5/3 divided by 2/3. Again, keep change flip, right? We get the square root of 5/3 times 3/2. 3's cancel, and I'm left with square root of 5/2, which is the reciprocal of the 2 over √5 we had above. But again, we got there by using only the data given, and so if we made a mistake on the previous part, we didn't just perpetuate our mistake. So as we can see, trigonometric identities are very useful to allow us to take minimal information like this. We have a sine and a cosine of an angle, and without even knowing the angle, we can know immediately what the tangent should be. So there is some power in what we're doing here. The last thing we're going to talk about is a notion of periodicity. Last lesson, we talked about coterminality. We said, for example, that pi over 4 is equivalent to, if I take pi over 4 and I add 2 pi to it. Therefore, pi over 4 is coterminal to 9 pi over 4. The reason why coterminality exists, of course, is that if you were to graph those angles, you get the same reference triangles. But if you get the same reference triangles, then of course, if you take the sine or cosine or tangent of those angles, you should get the same value. So what that means is that sine and cosine are now going to be referred to as periodic functions, where a period is the amount of time, the amount of input that elapses before you get the same value back. Meaning that pi over 4 the sine of pi over 4 and the sine of 9 pi over 4 are going to be the same, because 9 pi over 4 and pi over 4 are coterminal, meaning they're off by 2 pi. Algebraically, we'll represent that by saying that sine of any input x is the same as the sine of that input if you shift by 2 pi. Similarly, for cosine, if you shift by 2 pi, you get the same value as if you didn't shift. Of course, if these are true for sine and cosine, then they'll be true for secant and cosecant. And what's interesting is that the tangent, because it's the quotient of sine over cosine, it actually has a much smaller period. The period of tangent is actually only pi. So for tangent, it's not just coterminal angles that give you the same value. It's actually things that are sort of half coterminal. This can be really, really useful. For example, if you want to find the sine or cosine or the cotangent of an angle that is really, really, really big. If it's wrapping around and round and around and around so many times, what you can do is you can unwrap that angle, bring it back to reality, and then determine the sine and cosine of that. What do I mean by reality? Note, most normal angles are in somewhere between 0 to 2 pi. 0 to 2 pi, these are the angles, these are sort of the standard angles that we're working with. All of the angles that we drew in the last lesson with the pizza slices, they all lived from 0 to 2 pi. When we talked about coterminal angles, we did start finding angles outside of 2 pi. And then we had some negative angles, and we had some larger angles. But most often, you'll be more familiar with computing with angles that live inside of this region 0 to 2 pi. And so the whole point of this periodicity property is that you can take angles that don't live here, and then by either adding or subtracting 2 pi over and over and over again, you can find a coterminal angle that does live here, and therefore you can find its trig value a lot faster. For example, here we're going to do number 2 first. Notice that the angle in question here is theta equals negative 9 pi over 4. I don't know about you, but I don't know what this looks like. It's negative, so I know that we're graphing in a clockwise way, but 9 pi over 4 is not something I'm familiar with. I don't know what this means. So since it's negative, what I'm going to do is I'm just going to add 2 pi to it. I know that cosine, if I add 2 pi to the angle and build a coterminal angle, the cosines are going to be the same. So let's see if we can't bring this angle into a better light. So what we're going to do is we're going to note that cosine of negative 9 pi over 4 is equal to cosine of negative 9 pi over 4 plus 2 pi. Well, we can simplify that and we'll get cosine of, in this case, we'll get negative pi over 4. Now that is an angle I can actually draw. I know that it's going to be negative, so we're going to go clockwise. There's pi over 4 in the clockwise direction. That's negative pi over 4. We have ASTC. That's a 45-degree angle. So this is going to be a 1, a negative 1, and a square root of 2. So the cosine of that is going to be adjacent over hypotenuse. This is going to be 1 over square root of 2. So anytime you're given an angle that is borderline unintelligible, we can use the periodic property in order to add 2 pi. And if this was a really, really, really negative number, we could add 2 pi or 4 pi or 6 pi or 8 pi or however many multiples of 2 pi we want. In that same spirit, if instead we considered cotangent of 5 pi over 4, notice that 5 pi over 4, that is a normal angle by our definition, but somehow, if we were in quadrant 1, that might even be a little bit better. So what we might recognize is that cotangent has a period of pi. So what that means is that this is equal to the cotangent of 5 pi over 4 minus pi. If I add or subtract pi, the cotangent doesn't change, and so this is the same as the cotangent of just pi over 4. And somehow, pi over 4 makes me happier than 5 pi over 4. So now I can draw a picture, pi over 4 living in quadrant 1. Again, this is a 45-degree angle, so we have 1 square root of 2. And the cotangent of this is 1 over 1, otherwise known as 1. So this periodic property is really, really useful for sine and cosine. In particular, as we noted here, this type of question is basically embodying all of the techniques that we've developed so far. I can give you any angle I want now, make it as big or as small as I desire, and now you know how to find the sine, cosine, or tangent of that angle. By using the periodic property, you can bring it into the normal world, 0 to 2 pi, and once it's there, you can then turn around and draw it, build out a reference triangle, figure out the sine, cosine, tangent of that reference triangle, assuming it's a 30, 60, 90 or 45, 45, 90. So all of the techniques are coming together at this point. So I think that's a good stopping point. So we're going to go ahead and this will finish off this lesson on sections 4.2, 4.3, and 4.4. We've learned a lot of information at this point. In particular, we're pretty well versed with what trigonometric functions are, how to graph arbitrary angles, and how to compute the trig functions at those angles. We also talked about some basic properties of these trig functions, their domains, their ranges, periodicity, and parity. So there's a lot of information going on here, and there's a lot of practice to be had. So as you have learned all of these techniques, I hope that you've been taking a look at some of the homework problems that have been assigned and suggested, and I look forward to having continued conversations with all of you about sort of how one might employ the techniques that we've developed. So thank you for listening, and I'll catch you all in the next one.